That's too much. Anyway, we have the second lecture by Professor Randall. And let me say, we have the third lecture at 2 o'clock. Yeah. So right after lunch, the third lecture. Please.
Okay, can you hear me? Okay, great. Okay, so yesterday we talked about the signature that probably most people who've thought about RS are most familiar with, which is the resonance signature from a KK graviton, and it decays into all the standard model states, but that includes L plus, L minus, where those are leptons, and the leptons provide potentially, if the graviton is indeed light enough, and of course if it exists, a very nice, clean resonance signature. And we can even hope at the end of the day to try to do some angular measurements to determine the spin. We can try to reconstruct the mass squared of the resonance, and it should be very nice. Okay, so that's what we talked about last time. And then we started to talk about the fact that that isn't a robust signature for any implementation of this solution to the hierarchy. Right? The solution to the hierarchy relied on the Higgs being on the weak brane, a second brane in a warped extra dimension. And what we started to talk about last time was that the signature depended very strongly on the fact that the leptons were on the same brane where the Higgs resides. Okay? It's quite reasonable. It's not just an arbitrary thing we're doing to be difficult. It's actually quite likely that if this is in fact the solution to the hierarchy problem, that fermions and gauge bosons are not just sitting on the weak brane, but they're in the bulk. That is to say, they're in the higher dimensional space. And the two reasons we thought this is a possibility is, one, it naturally gives unification. That's, you can take it or leave it, but it is a possibility that you can get unification in this scenario. But the second reason, which I find quite compelling, is that it gives a natural, or it seems to give a natural explanation of quark masses and mixing angles. And that's work that I and others have done, and I'm going to talk a lot more about that in the third lecture, just why I think we can get flavor structure from extra dimensions in a quite compelling way. But that's only true when the fermions are in the bulk. And of course, if the fermions are in the bulk, because they're charged under various gauge symmetries, the gauge bosons also have to be in the bulk. Okay? So this is not just some arbitrary, like, quirky corner of parameter space. It's actually a model, a way of looking at RS that many people even think is more likely. Of course, I'm not going to decide which is more or less likely, but I'd say that it's as reasonable a thing to study as is the model where everything is on the brane. Okay? So that means we really have to think hard about what the signatures will be in this case. And just right from the get-go, you realize that you're going to have a problem, because we relied on the light quarks and gluons to make the graviton KK mode. The light quarks are now localized away from where the KK modes are. Moreover, the leptons, the charged leptons that we were relying on to reconstruct the KK modes, lie away from where the KK modes are, again, because the leptons, of course, are very light, so you would expect them to have a small wave function on the IR brane, okay, on the TeV brane, where the KK modes are. So we really have a very different scenario from the point of view of actually identifying this theory, if it exists, okay? We still believe that there are resonances. We talked last time about what we could do with the KK graviton resonance, but we observed that, first of all, the production cross-section is lower because the gluon, which is the only way we can produce it, is spread throughout the bulk, so we're suppressed by a volume factor. And furthermore, the decays won't be into these nice lepton pairs, but it'll be into TT bar, okay? And that's basically where we left it last time. We said we left it that the maximal reach you would expect for a KK graviton is probably a couple of TeV, when the mass is still light enough that we can hope to identify TT bar through its decays and reconstruct the tops, but it's not a very high reach, okay? So that was what we talked about last time. So we talked about identifying the KK graviton, okay? So are there any questions on anything from last time or up to this point? Okay. So what I want to do today is in the first part of the talk about a more promising mode to look at. People have done phenomenology of other modes, but I'm going to focus on the KK gluon, the Kaluza-Klein mode of the gluon. Last time we did the Kaluza-Klein mode of the graviton, because the graviton was the thing that was in the bulk when everything is on the brain. But now we have everything in the bulk. There'll be other KK modes to consider, and one of them is, in fact, the KK gluon. So just to remind you, we had several wave functions we want to think about here. We have the KK graviton peaked. The graviton modes we're interested in are always peaked in the TeV brain, the TeV region. That's true for the KK graviton, and that's true for the KK gluon. Okay? The difference in the KK gluon that we emphasized last time was this fact that it has this long, flat region. So even wave functions that are localized near the Planck brain will have a not insignificant coupling to the KK gluon. Not true for the KK graviton, but it is true for the KK gluon. The gluon itself was just the flat mode that's spread throughout the bulk. Okay? And what we want to focus today, right now, is on this KK gluon, the one that's in pink, that has this flat shape and then this peaked shape towards the TeV brain. Okay? That's what we're going to talk about looking for. Okay. So we went through the graviton already, so I'm skipping that now. And we're going to come to the gluon. I guess I could have started there. Okay. So why is the KK gluon of interest? Well, as I said, it's peaked on the TeV brain, but it's relatively flat in the bulk. It turns out that that flat region gives you an interaction strength that's about suppressed. It is suppressed, but it's suppressed by the square root of the volume. The volume being the size of the extra dimension, which means it's suppressed by a factor of roughly 5 or 6, rather than a factor of 35, which is what was true for the graviton. So it's a bigger interaction strength when we have. Of course, from the gluon itself, you have no interaction because the gluon itself, the zero mode gluon, the one that really mediates QCD, is orthogonal to the KK gluon. So it's only the interaction with these light quarks that's relevant for the production cross-section. There's a few other things that might make it more advantageous to look for this. The KK gluon might well be lighter, and there's no suppression by a Planck scale. So we anticipate a much larger reach for the KK gluon. That is to say, up to higher masses. Okay? We think we can find the KK gluon up to heavier masses. And this is just to say it goes like 1 over the square root of the volume, which is the fact I just said a minute ago. So we'll skip this. And this is what the KK gluon looks like in a little more detail. I had a heuristic plot before. But this value here is about negative 0.2. Okay? So when we were doing this project, we had the surprising thing that this coupling remained at minus 0.2. We didn't know what was going on. But this is really the shape of the KK gluon. Okay? So it really hasn't. So no matter how peaked in the UV, that is to say, no matter how light your quark is, you still have an interaction with this KK gluon. That's only about a fifth of just an ordinary gluon interaction strength. Of course, something localized in this region, which, as we know, is the top right, okay, the heavy top is localized here, has a bigger than strong interaction strength because it's so peaked here. It's going to be multiplied by 5. So you're going to have a huge interaction strength with the top right. But to actually produce the KK gluon, we have to rely on this coupling, which is not insignificant. It's 0.2 times J. Okay? And this is another way of saying that. Let me explain this plot. So remember this parameter nu. I talked about it last time. You might not remember. Nu was related to the bulk mass divided by k. The bulk mass of the fermion divided by k, where k set that exponential, e to the minus kr. K is also set in the energy in the bulk. Okay? And you might recall that this parameter m over k, when it was bigger than minus 0.5, you get localization on the IR brain, the TeV brain. When it was less than minus 0.5, you get localized in the UV. And so this is exactly what we were saying in a different way in the previous transparency. Because what you see here is that when you're localized in the IR, you get a bigger than strong interaction strength, multiplied by 5 or 6. Whereas if it's localized in the UV, you get this interaction strength that's about 0.2 of the strong coupling. So it's always rather significant, but it's of course much bigger if you're localized where the KK mode is localized. Okay? Are there questions on that? Yeah.
Why do you need a KK gluon when you already have gluons? What is the difference? Is the KK gluon one that also is mediating the forces between quarks?
Well, we need a KK gluon if we believe that we have fermions in the bulk. That if we're going to try to explain the flavor of quarks or unification by putting fermions in the bulk, we have to put gauge bosons in the bulk. Once gauge bosons in the bulk, it's not up to us. I mean, there is a KK gluon. It's not necessary. In fact, we have to make sure we don't generate interactions that we don't want, particularly flavor-changing interactions, which we'll talk more about in the next lecture. But they're there once we decided to look at a model with fermions and gauge bosons in the bulk. And as I've tried to emphasize, it's not just a corner of parameter space. There is a very strong motivation to think that the fermions and gauge bosons can be in the bulk, even if this warped geometry is a solution to the hierarchy problem. Okay, so it's just there. Okay? Other questions? In the back.
What happens at the zero transition?
What happens where?
At the zero transition in this plot.
The zero transition. Do you mean here? Yeah. What happens is eventually you have an intermediate regime where you have actually a flat wave function. So you first are local. So for these values, you're localized in the UV. At this point, you're going to just have a flat wave function equally distributed everywhere, and then you're localized in the IR. Okay. Yes?
So, sorry for getting back, one step back. But can you go back to explain us a little bit how QCD ray is unchanged? Because now you have a gluon in the bulk, right? Mm-hmm. And U and D quarks are slanted towards the Planck ray.
Right, so that was why it was...
Sorry for...
That's okay, it's an important point.
Before.
That's why I'm asking for questions while I'm talking, because if you get lost in the middle, it doesn't help. Okay, because you have the gluon wave function, and that's why this gluon is exactly flat. Okay? The fact that the gluon is exactly flat means that independent of the wave function, the normalization is just 1. So independent of what your wave function is, you will have the same interaction strength with the zero-mode gluon. Not true for the KK gluon, which has a non-trivial shape, but it's true for the zero-mode gluon, the one that mediates QCD. Okay? Other questions? Okay. Okay, so then, before we do any cuts, before we do any questions about whether we see the final state, this is what you get for the cross-section. And you see it's much bigger than what we had before for the KK graviton. And it's quite reasonable to think that this is sigma and picoborns. It's quite reasonable to think that you can get up to, even 6 or 7 TeV according to this, right? The cross-section is really big. And then the question becomes, will we actually see these things? Okay, this is just the cross-section. It says there's a lot of them. So now we have to ask ourselves, can we find them? Okay, if they're there, we will be making them at the LHC. So it's really important to know, is there going to be a way to find them? Okay, and that's what we want to talk about next. And that's returning to the general lesson that we talked about in the very beginning of last talk. We want to make sure that we are ready for whatever signal is there. This is quite a reasonable possibility, and are the searchers ready to find it? Okay. So the first thing to check is, does it dominate over just the top background? Okay? As we've emphasized several times, this KK gluon will decay into TT bar. It's localized on the TV brain. That is a much bigger cross-section to decay into TT bar. Okay? And what do we see? Well, we see that if we have the top background, okay, so this is for a mass of 2 TeV, 3 TeV, 5 TeV, and 7 TeV, we do see a difference over background. Okay, of course, there's all sorts of effects that this doesn't include. This is just a simple Monte Carlo study, but it looks promising. It looks like if we can see that we have TT bar in the final state, the resonance will dominate over the background. It's a broad resonance, but it still dominates over the background, and hopefully we can see it. Okay? However, suppose we don't know that those jets are top jets. Suppose we didn't figure out that those are top jets. Would we still be able to find it? The answer is absolutely not. Because this is the jet background, right? This is all jets. It's not just top jets. And that completely swamps any signal we might hope to have. Okay? So the point I want to drive home here is that we want to be able to find tops, not just at low energy, but at high energy, if we want to have any hope of identifying and finding this KK gluon. And I think, and Some of you might be skeptical about this particular model. I mean, I think it's quite a reasonable thing to look for, but I think this is actually a very important lesson. I mean, I was very surprised to realize this hadn't been really investigated, because as I said in the last lecture, the top quark is the heavy quark. It is the most strongly coupled to the electroweak sector. So whatever the electroweak sector is, if it's any kind of strongly interacting theory, you want to be able to find energetic tops and identify them, because they will give you the best clue as to the electroweak sector, which after all is what the LHC is designed to explore. Okay. So how are we going to find the tops? Well, we can ask the question, can we use this DR that we talked about last time, which is to say, can we just look for separation in the decay products? Well, let's just take a look. So we need this to be bigger than 0.4, okay? Here, this is for the lepton and the B, but this is generally true. Remember, the reason we lose the separation as it gets energetic is they become more and more collimated. As we look at higher and higher energy top jets, things are more boosted. So we had a top decay that had nicely separated products. As it gets boosted, they all become very collimated. Okay? So if it's 1 TeV, okay, if substantial fraction is less than 0.4, and we're fine. 3 TeV is getting kind of borderline. We're kind of right at the borderline where, you know, maybe half or less than 0.4, half gram. But once we get bigger than 3 TeV, forget it. It's just hopeless. We're going to have all the events are going to be in the region. This is 8 TeV here. All the events are in the region less than 0.4 essentially. So we cannot use the standard way of looking for tops by looking for these separated prongs in their decay. Okay. This is a very busy plot. What we did is we just asked for the fraction of events for certain numbers of distinct objects for events from decay of a KK gluon. So in other words, we looked at the different masses. We said, how many final states do you see? How many do you actually see these separated products? And essentially, the message of this plot is the same as the message of the other plot, which is once you get up to 4 TeV, essentially none of the events look like multi-jet events. All these jets are going to merge. So you're going to basically have 2 jet events at the end of the day. Almost all the events will be 2 jets once you get to heavy enough KK gluons. Okay? And this is the same thing where we have a leptonic decay. And the message is the same. Once you get to masses bigger than 2 or 3 TeV, you just are not going to be able to use the separation of the decay products to identify the tops. Okay? So what are we going to do? Well, maybe a top jet mass measurement. That's really hard. More likely is detailed substructure of jets, hard lepton, or just the structure of jets. And people are beginning to do that. In fact, some of my collaborators on this project have begun to look at ways to do this. I think it's one of the most important studies to be done that remains for the experiments right now. It was beyond what we did in our paper, and I have not done work on this, but I've thought about several methods and talked to people to try to get a sense of what's going on. One thing we did do is we just said, what is the accuracy with which the determination is required? And what we found essentially was that we needed to basically have at most about a 10% contamination from ordinary jets into top jets if we're going to hope to see anything, at least in this KK gluon mode. So it's a one way of sort of putting some benchmark. I mean, whatever method we have for identifying tops, there's going to be some contamination from ordinary jets, and this basically sets a scale for how well we want to do. Okay? These are a couple of sidelines. I'm not going to go into all the details, but it's in the paper if anyone is interested. One of the interesting things to do, if we really do identify these tops, will be to do a spin determination, because according to this model, it should be mostly top right. So doing some angular measurements would be very interesting to see if we could. This is with spin determination, but also to determine that it's a top right is very interesting. So the summary is, of course, that this weak scale physics in the form of KK modes should be testable. The best signature, of course, is the spin-2 resonance and mass gap that you get if everything goes on the brane. But in the bulk, it's going to be the KK gluon mode that we're going to have to look at. And the decay into tops is critical. And I really think this is incredibly important to really see how high energy we can push this top identification. Because as we see, the barrier is not the cross-section. The cross-section is plenty big. The barrier will really be when can we identify top jets and distinguish them from ordinary jets. So I think there's a lot of work to be done in this, just really thinking about what the jet characteristics are when they come from a top. I mean, they will be different, because instead of just radiating, I mean, an ordinary jet, you're just radiating gluons. In this case, you really are starting with separated things that are getting merged. So the energy distribution among this, in the initial stages at least, are going to be fairly similarly distributed among the various clumps inside. So maybe you can look at detailed substructure, and I know people who are doing that. I think another important question that's only been looked at a little bit is just how high energy we can really push B-tagging. Of course, B-tagging becomes less and less efficient as those tops become more energetic, but I think it's really an important study to do to really push it. And to explore hard leptons as well. Of course, if the W decays with the lepton, that could be very interesting, but again, there's going to be a lot of contamination from punch-through, even from muons. So again, this is a really important study to do. So I think all these different ways of actually seeing how high energy we can push these detectors are incredibly important. So to conclude this part of the talk, we will be able to tell things, but we really have to work hard to get the KK gluon better. There will be some KK graviton signal if it's sufficiently low scale, but the real challenge is going to be this top quark ID. Okay, so that's it for the KK resonance part of the talk. And what I'm going to do for the next half hour is talk about black holes. So while I'm fiddling around here, why don't you guys see if you have any questions? Okay, just shout it out while I'm doing this.
Is there any hope for production of one of these KK gluons with something else that would help with that signature, or is it really just going to be the KK gluon to TT bar and not much else in the event?
For those particular events, I think it's really going to just be TT bar. Mm-hmm. People are thinking about other ways that you might, other things you might hope to look for. In addition to the KK modes I've talked about, the radion, which was mentioned yesterday, some of these models have funny, heavy quarks, top quarks or B quarks, and those could provide, yesterday there's a Monte Carlo workshop going on, someone talked about looking at like sign leptons but these are very model dependent. But there could be sort of heavy bottom quarks, which would be extremely interesting to look for if in fact they exist. So I think the best bet is going to be sort of to supplement it. I mean, maybe we're missing something. Maybe there's some other way of doing it. But I think, and as I said, I'm not only interested in KK gluons, although I think it's very important. I think just identifying these energetic top quarks is independently incredibly important. Other questions? Yes?
Is there any reason that the mass of the KK gluon couldn't be below 1 TeV?
Well, there are already bounds on KK graviton and KK gluons. I mean, people have done searches. Okay, so one of the reasons is because of existing bounds from the Tevatron on KK resonances. It's only about 500 GeV at this point. That's one reason. Another reason is all sorts of precision constraints and flavor constraints. You really have to worry about those because if the KK resonances are light, then you have exchange of KK resonances. You have to make sure you don't generate bad flavor changing effects, things that are in violation of precision electroweak. So it gets very dangerous to have them to be too light. I mean, it doesn't mean it's not worth looking for, but we really expect them to be somewhat heavier, is the fact. I mean, of course, from the point of view of naturalness, we would like it to be that low, but it just seems like there are too many constraints. It's very unlikely to be that low. Okay. Other questions? Yes?
Do the standard model particles in the bulk require KK modes, and if so,
can you
what are
speak more clearly?
Sorry, do the standard model particles in the bulk acquire KK modes, and if so, what are their properties? What are they like?
Yeah, so you have things, absolutely. So you could have a KK mode of a top, for example, which could decay via a Z into an ordinary top, for example. So that might be an interesting thing to look for. And like I said, there are these heavy quarks. So there are other studies being done about things like that. Those are model dependent because there might be other ways that those particles can decay. But those are very interesting studies to be done, and some of them have been done already. But I'm not talking about it here. I don't think they're necessarily the most robust or easy signatures, but I think it's actually really important and interesting to look at that as well. In that case, of course, you'd want to identify tops again. Okay. Other questions?
I have a question. So how about the couplings among those KK modes? I mean, for instance, the KK gluon just coupling with some KK graviton, and KK graviton can decay to some electron or positron.
I'm sorry, I really can't hear you.
I mean, how about the coupling among the KK modes? I mean, for instance, is that possible that the KK gluon could decay to KK graviton, and the KK graviton decay to some
can the KK gluon decay to KK graviton? As you saw, the mass was only about, the KK gluon looked like it was about 1.5 times lighter than the KK graviton. Of course, that assumed no brane kinetic terms, so there are variations of that, but it's very likely that the KK gluon is too light to decay into the KK gravitons.
I mean, the KK graviton is just an example, so how about other KK mode?
I'm sorry?
The KK graviton is just an example, so how about the KK other particles, since the leptons and some leptons and some vector bosons are existing in the bulk, and they have some KK modes. I mean, is it possible the KK gluon decay to some other KK vector
as I
boson?
showed in the plot before, most of the, I mean, just if you don't have brane kinetic terms, the KK gluon is probably lighter than a lot of those other KK modes. But it's certainly worth looking at whether these decays can occur. I haven't thought about it a whole lot. But there are conceivably, if you have large brane kinetic terms, there are conceivably other modes involving the fermions of decay, which I haven't thought about because they're not as likely. I've been focusing on sort of the dominant, most robust signatures. But there is the possibility that there could be other KK modes that would become interesting to study as well. And that's all work that should be done. Okay. So should we go on? Okay, so what I wanted to talk about for the next half an hour, or 20 minutes, whatever it is, I wanted to talk about my thoughts about black holes and quantum gravity at the LHC. And this study doesn't apply only to the type of warp geometry that I've been talking about. It applies also to large extra dimensions. And it refers to this idea that there's this strong possibility that if there is a low quantum gravity scale in higher dimensions, there is the possibility of making black holes at the LHC, which of course it's very exciting to some people, very upsetting and worrisome to others, and actually just an interesting physics problem for those of us in the audience here. Okay, so the question is, will we actually make these black holes? And what I want to argue, and this is work I did with Patrick Mead, is that it's really unlikely we're going to make black holes. I mean, black holes being what people think of when they think of black holes, and I'll describe what that means. But there are going to be some very interesting compositeness studies that we can do to really probe the low quantum gravity scale. They're in some ways perhaps even more interesting because they can shed some light on what is actually going on with quantum gravity. So let me tell you about that a little bit. I talked about this already, so some of you might have heard it about a year ago, but I'm just going to go over it again. Okay, so this is what I just said. One of the most anticipated signals at the LHC has been these small higher dimensional black holes. Give a public lecture, someone always asks about it. Higher dimensional gravity is about a TeV. We can have the center of mass collisions at the LHC, which is really of order this quantum gravity scale. So it looks like the conditions are met for small higher dimensional black hole formation. In particular, you collide together quarks, sometimes spelled wrong. And in the central region, you might actually have these two get within their Schwarzschild radius. You might have necessary energy for a black hole contained within the Schwarzschild radius. And if that's true, you expect to get a black hole. That's what classical general relativity tells us, that if you get two things with enough energy inside their Schwarzschild radius, you'll form a black hole. Okay? And it really looks incredibly promising when you look at it at first. The cross-section goes like the Schwarzschild radius squared. That is to say, there's no phase-space suppression factors, there's no small coupling, it's just geometric, it looks enormous. And you can write it in terms of the black hole, in terms of the quantum gravity scale, and E, which is basically the mass of your black hole. And if you say that M is about a TeV, it looks like you have 100 picobarn cross-section, absolutely enormous. So it looks like, first of all, you have this prolific production. Furthermore, it's supposed to be this amazing final state because you're going to get this large number of particles spherically distributed in all directions, characteristic of Hawking radiation. So that was the claim. That's what people said is going to be formed. Okay? So in this talk, or in the remaining part of this talk, I want to talk about how much of it is true. Do we even really produce black holes? And what I'm going to argue is that the LHC is very unlikely to really make these. I mean, you can look for them if you want, but I think it's pretty unlikely given the constraints we have. And these multi-particle final states are even more unlikely, even if you have something that you think is a black hole. You're just not going to get to high enough energy, which is equivalent to high enough entropy, to really make these multi-particle final states. However, what I really want to emphasize is that even if what I'm saying is true, and I do believe it's true, all is not lost, because potentially there were much more prolifically produced two-body final states. Not these multi-particle final states that people talk about when they talk about black holes, but really some interesting two-body scattering. And although it's uncalculable, I'm not claiming we can predict it because it will be in the quantum gravity regime. It's an extremely interesting thing to study experimentally. And what I'm going to try to show you is that different models of quantum gravity give very different cross-sections as a function of energy, very different angular distributions as a function of energy, so that we really can actually learn something by studying this question not theoretically but experimentally. Okay? So that's going to be the point of this next part of the talk. And again, this is the general lesson. We want to make sure not only that we're optimizing existing searches, but are we doing all the searches possible? And I really think that compositeness searches are sort of underrated. And we sort of dismiss strongly interacting theories, but I think there's a lot of information that we can get from compositeness searches. And again, one of the things I'm trying to emphasize is trying to maximize energy reach. And again, for lots of interesting physics, compositeness searches can be an interesting way to get at them, even if we don't see the particles themselves. Preliminaries, we're going to consider ADD, which is Arkani-Hamed-Dimopoulos-Dvali, which are large extra-dimension black holes, as well as the black holes from the type of theories I did with Raman Sundram that I've been talking about before. There's large extra dimensions. I didn't emphasize this in my talk for one thing because I really think it's kind of unlikely, because I think this large volume is unlikely, and because there's very strong cosmological constraints on this model. But this is really the model that was sort of mostly motivating this black hole idea. And the idea is that the large Planck scale is related to a low quantum gravity scale of TeV through a volume factor. And so what we're going to do is we're going to look at this model, we're going to put in the experimental constraints so that we can see what this scale should have said MD has to be. And experimentally, we're going to do the most conservative case, which is n equals 6, which is the most conservative. N is the number of extra dimensions. And in that case, you have a bound of about 900 GeV. If we looked at smaller n, you would have an even higher bound on MD, which means it's even more unlikely to produce these black holes. Okay? It's only when MD is small enough that it's kinematically accessible that we can really hope to make these black holes. Okay? I just want to point out that although it's been not talked about a lot, there's also the possibility when all the particles are on the weak brane that in the RS scenario, you can also make higher dimensional black holes, in fact 5-dimensional black holes, because there's basically a warped Planck scale that applies for 5-dimensional gravity near the weak brane. And it's not usually considered, when people talk about black holes in the context of RS, they talk about physical black holes, which are sort of pancake-shaped things that I'm not going to talk about here. And they talk about strong bound states, characteristic of anti-de Sitter space, which I'm not going to go into here. But what I do want to emphasize is that there is a mass region. This parameter m is the cutoff scale having to do with quantum gravity. K is this curvature scale that I've mentioned many times. And there's this intermediate regime where you have a hope of making things that are essentially flat space black holes, which is the one kind of black holes we're interested in. So even though we know we have this very warped space, there's this sort of intermediate energy regime where you have the chance of making these black holes. So we will talk about 5-dimensional black holes as well as these 10-dimensional black holes. And m is greater than 500 GeV from an experimental bound, okay, on the KK masses. Okay? I'm going to skip that. But I'm going to ask the question, why is our estimate so remarkably different from what I said in the beginning, which is what people were saying before? And I should say that the theory has evolved since the time people first proposed black holes. So we weren't the first people to say everything that we're saying, but we kind of just put it all together and asked, what can we really expect? So at what energy is a black hole actually created? The point that I want to make is that the estimate was always optimistic. Okay? The reason it's optimistic has to do with the fact that, as you all know, PDFs drop rapidly. So it's very critical that you actually get the threshold right. If you said black holes are formed not at the scale m, but at the scale 4m, okay, that doesn't sound that different from the point of view of just some rough estimate. But as you know, from the point of view of an experiment, there's a huge difference between having a threshold of 2 TeV and 8 TeV, okay? So it's really important to get this threshold right, up to these small factors, which we can't actually do, but we can sort of estimate what it is. And I'm going to show you that this threshold is always probably going to be at least a factor of few. So getting the threshold right is really important because the PDFs drop so rapidly. Quarks and gluons carry only a fraction of the energy of the protons. So the rate depends dramatically on the threshold. Okay? So if we really want to understand that original estimate I gave you, we have to consider the terms in it very carefully. And there were only 2 quantities. There was m, which is the quantum gravity scale for higher dimensions, and there was m black hole, which was E in the original formula I gave you. And we have to understand basically when that threshold really occurs. Okay? So I have a lot of details here, and I don't think I'm going to show all of them to you, but I want to give you the flavor of the kinds of things we thought about. And please stop me and ask questions if you want me to talk in more detail. So the first point I want to make is that M, the gravity scale, is convention dependent. So depending on who you are, you can be off by a factor of even 3, depending on how you've defined your quantum gravity scale, which has to do with the normalization in the Lagrangian of the curvature term. Okay? So one person's TeV scale is going to be another person's 3 TeV scale. So clearly you just have to get the convention right. This was not something impossible, but it was just a nuisance when we were doing this project. The other thing is, where is really the thermal black hole threshold? When do we really start forming black holes? Okay? What scale above M can we really say we're making black holes? And one related question is how much energy you need. But what is this threshold black hole mass? So when do we have a black hole? Well, clearly we want to be bigger than the gravity scale. And as I said before, that's not even a convention-independent quantity. So clearly this isn't a robust criterion, but it gives you some rough idea. A slightly more and equally convention-dependent criterion, but maybe a slightly more robust condition might be the Compton radius is inside the Schwarzschild radius, which sounds quite reasonable. This is the Compton radius, this is the Schwarzschild radius, but you see it's a much more stringent version of the above. It already says M black hole is greater than 4M if you're looking at these large extra-dimensional black holes. And in our case, RS case, it's bigger than 16M, which remember is already at 8 TeV. Their bound was 900 GeV, so this is already about 4 TeV. So this is saying that that threshold is already at least 4 TeV if you believe this simple criterion, okay? Which is hard to imagine isn't true, okay? So it's saying the threshold is significantly higher. Significant from the point of view of experiment, not that significant from the point of view of theory, but really, in terms of search, it's really important. Okay. Now, there's a lot of additional criteria, which I don't think I have time to go through in detail, but there's going to be a model-dependent constraint on the black hole mass versus brain tension, because we don't want a big back reaction from the brain on these higher dimensional black holes. We really want the black holes to be thermal, which is really important. That is to say, when you form black holes, we know black holes carry entropy, and that entropy goes away as they decay. You really want to be enough above threshold that you can really safely say you have a lot of degrees of freedom, so you can really think about it like a thermal object. No one's going to say something that has 3 degrees of freedom is thermal. Okay? You really want it, and one way of thinking about thermality is that no individual degree of freedom is carrying a large fraction of the black hole mass. So if you were to radiate a single particle, you don't want to find the effect of temperature changing dramatically or the effect of energy changing dramatically. So these are all kind of rough criteria, but they're all very reasonable criteria, and you can apply them rather conservatively. Another criterion is that you want the black hole lifetime greater than the Schwarzschild radius, so that the black hole isn't changing a lot as it decays. So as I said, these aren't sharp criteria, but they're certainly minimal essential requirements. Okay? And these are details of working that out, but that's basically the physics that went into it. We really wanted to have these criteria saying that if we define a quantity x min, which is where the threshold mass is in relation to whatever convention-dependent M you have, that you really want to be able to say that you're safely above some black hole threshold where you can really form a thermal black hole. Okay? And I'm not going to go through all the details. But I am going to show you these plots, which tell you that you really need x min to be about 3, at least in both ADD and RS. This is independent of the criteria I talked about with Compton radius and Schwarzschild radius. We really need at least a factor of a few over threshold in either model, or else just the criteria are just way not satisfied. So even that, and that's really very generous. I mean, we'd really want x min to be higher in most cases for any reasonable criterion. So we conclude that x min should be reasonably high, that is to say at least a factor of a few. And it's another important point that even if you did make a black hole, having this x min tells you that you can't really extract fundamental parameters, since we don't really know exactly what that x min is. So even if you found some black hole threshold, it would be hard to interpret. In addition to this fact, which was that the threshold energy is probably higher than M, there's another problem, which is that not all the energy of the collision gets trapped behind the horizon to give you a black hole, which is referred to as inelasticity. Okay? So we know the energy has to be at least x min M, but that doesn't mean that we really need center of mass energy x min M, because not all that energy is going in. So you need an even higher energy in order to have enough energy trapped behind the horizon. Okay? And so this is some work that people have done classical calculations to determine how much of the energy really gets trapped behind the horizon. And again, I'm not going to go through all the details, but I'm going to show you these plots, which give you sort of inelasticity as a function of impact parameter. That is to say, the distance between those two at minimum distance, colliding quarks. And you see that as you get out to the Schwarzschild radius, you basically get no energy trapped behind the horizon in either d equals 10 or d equals 5, that is to say ADD or RS. And even when you're at zero impact parameter, you're not getting all the energy trapped behind. You're really not. And again, this doesn't look like a big effect, but it's an enormous effect, because what it effectively does is tell you your black hole threshold is higher than you had thought. So again, this translates into an even higher threshold, because you need to have that much more energy so that the fraction of energy that gets trapped is enough to make a black hole. And if you work out what the cross-sections are, including the effects of inelasticity, you find that they go way down, factor of 1,000, depending on various parameters in the theory, which I'm not going to go into. But the dotted lines are without inelasticity, the solid lines are with inelasticity. So your cross-sections are enormously suppressed by including this inelasticity effect. Okay. So the upshot is that M black hole threshold is far higher than was thought. So it really means that you're just probably not going to produce classical thermal black holes. Okay. So what I'm going to do now is ask, what are we producing? What would be the final state? I mean, you're going to have this collision. Something presumably is happening. So what do we think is going to happen, and what's going to come out? So again, this is in the quantum gravity regime. We can't calculate. So we said, how can we at least estimate or try to approximate what's going on? So we said, well, let's take this black hole thing a little seriously and look at what the average number of particles that come out are. We said we're not far above threshold. So what are we actually producing? And what we found is, so what we asked is, how many times do we have 6 particles in the final state versus how many times do we have 2 particles in the final state? So let me skip this plot and show you this one, which is a function of x min and md, or m. So what we have are the solid line are black holes that would decay primarily to 2-body final states, whereas this other line is 6-body final states. So what I'm trying to show you is that most of the time, the parameter space is covered if we just look at 2-body final states. It's only in very extreme circumstances that we can expect even 6 particles. We're certainly not getting fireball states with many particles in the final state. But even if we ask very conservatively for 6-particle final states, it's still going to be pretty much dominated by 2-particle final states. So what does this mean? It means we're not making classical black holes. And 6 particles really isn't enough for a classical black hole. And even then, it's not dominating. So what we decided to do is just face the facts. We said, we're not making black holes. But we are getting these interesting scatterings because we do have this strong higher dimensional gravity effect. But it's probably only going to appear in 2-body final states. That is to say, 2 jets or 2 leptons. So we asked, can we distinguish this from background? Is it just like QCD, or is it different? And the answer is yes, it can be very different if gravity plays a role. And transversality is going to be key, because we would expect, black hole, you have more sphericity. What that translates into in terms of 2 jet events is that they're more transverse than QCD, which tends to be very longitudinal. So what we're going to talk about now is the possibility of probing quantum gravity by looking essentially at compositeness studies, but really focusing on this transversality as a function of energy to see, can we distinguish different quantum gravity models. In addition to the transversality of the jets, the relative rates of leptons and jets could be very different if gravity is playing a role. So I'm going to talk about that as well. Question over here.
About multiplicity coming from the black hole decay, how do you, for example, compute the multiplicity coming from the final stage of the decay?
So what we said is we just took seriously the thermal radiation. The multiplicity from the final state, that's not a black hole anyway. Okay? The only thing that really is supposed to be associated with true black holes is the thermal radiation. And so our point was that just this alone is probably, so this is this was just enough to get rid of everything. You have to, in order, okay, so let me backtrack. The picture that everyone who works on black holes has is there's some sort of spin down, then there's some thermal radiation, and then there's some remnant. What I'm saying is that you've already lost all the energy just by decaying into a few particles. There's no remnant at the end. You've just basically have a few particles in the final state. So you're going to so it's just the way it's been incorporated in the Monte Carlos, on the most part, doesn't even see this, because you assume that there's a remnant with 2 particles, so you have 2 particles plus thermal radiation. What we're saying is most of the time it looks like you really just have 2 particles in the final state. I don't expect it to be some thermal object that becomes some remnant. It's really just some scattering process is really what's going on most of the time. I mean, again, this is quantum gravity, we can't calculate, but there's no reason to think that anything else is going on, given the energy reach that the LHC has. If we had a higher energy reach, then we could start talking about those things. But it looks like, given this energy reach, what you really have are just some scattering processes. And it's not, even if there's something that's sort of pseudo-resonance-like, it's not like there's some stable remnant, which then gives you some additional particles. And there's no thermal radiation. It's just really just something that's going to decay with some sort of resonance-like behavior.
I think I should emphasize that the fate of this remnant we just don't know. It can decay or it can be stable.
But what I'm emphasizing is that, if you really want to do these Monte Carlos, one possibility is that remnant has no particles in the final state. Because the thing is, you're never going to see this 2-body final state, because you're always going to have at least 2 particles from the remnant, plus whatever thermal radiation there is. What I'm saying is that a lot of the time, I think it's just going to be 2 particles. Okay? So that you wouldn't even see this in the Monte Carlos the way they're designed right now. Which is very important, actually. Okay. Are there questions before I go on? Okay. So what's the search we're suggesting? We're saying just look for 2 jets and 2 leptons in the final state from whatever was there. It's not necessarily a black hole, but it's some interaction that happens because we have low-scale quantum gravity. What should you measure? Well, cross-section and angular dependence as a function of the energy. And we want to look for distinctive characteristics in both the energy and angle dependence. And to show you that this could be interesting, I'm going to consider different models for quantum gravity. I'm not telling you these are predictions from any particular theory. I'm saying these are models of quantum gravity, and I want to show that they can give qualitatively interesting results. Okay. And we're going to use this parameter R eta, which has been used to do compositeness studies. This isn't necessarily completely optimized, but this was something that was used at D0. And it's the number of events with eta between 0 and 0.5 versus the number of events between 0.5 and 1. And what this does is it's a number that measures transversality. And one of the reasons it's nice is some of the systematics cancel in this ratio. Okay? So it's a very nice measure to see, are your events more transverse than standard model. And in the standard model, you're dominated by T-channel gluon exchange, and you can calculate it, and you basically at R equals 0.6. So what we're looking for are deviations from R equals 0.6. Because the cross-section, as you all know, might be messed up because of energy mismeasurement or something of that nature. But if we have this fairly robust transversality measure, in addition to the cross-section measure, we really can hope to make progress and see new physics. And again, I think people were confused when I gave a talk. These are just models of quantum gravity. We're just trying to take advantage of the rich data and ask, what are the distinguishing features? What should we be looking for that experimentally probe quantum gravity? Okay, so here's a model. Okay, it's very crude. But we said, suppose the cross-section was the same as the cross-section you get for black holes, but we're not saying they're black holes, we're just saying they're 2-body final states. Okay? So that's where these cross-sections come from. So the upper plot is cross-section. The lower plot is this parameter R. Okay? And what we have are various scales M. We have a very crude model where we just say black hole production starts at the scale M. Very, very crude. But you see that if you really had the cross-section as big as is predictive of black holes, it is well above the QCD background. Even so, you might be worried that you just didn't compute the QCD background correctly. So it's useful to look at this quantity R that tells you about this transversality. And what you see is as soon as you make something that looks like black holes, because they are effectively spherical, your R parameter will be much higher than the standard model, which we said is 0.6, and this includes experimental errors. The left-hand side is for ADD, the right-hand side is for RS. And in both cases, you see that you would find jets that are much, much harder than you would get if it was just QCD. So it's certainly been an indication that something was there. Is it black holes? We don't know. But one of the things that looks characteristic of a black hole is probably some sort of hard turn-on of the cross-section. So we don't know exactly what the threshold behavior is, but this is a very characteristic behavior if the cross-sections at all are related to what we get for black holes. Okay. What's another model of quantum gravity? Well, string theory is another model of quantum gravity. We don't know if it's right, but it's another model. If these ideas are right, we have a low quantum gravity scale. It's possible we have perturbative string theory even below that quantum gravity scale. So what would happen if we had string theory? Well, we can model it with the Veneziano amplitude. And what that would tell us is that if we have perturbative string theory, we actually expect resonance behavior. And then we expect a dramatic drop in the transversality. Remember, one of the goals of string theory was to have softer collisions when particles collide together. So if you get into well into the string regime, you would expect this transversality to actually go down below what you get in the standard model. So let me show you what we got. So there are various parameters for the width and various parameters for the string scale assumed. But what you see is you get precisely this sort of thing. This is a standard model cross-section, and here are some string resonances that you might hope to see. But look at the parameter R. It starts off a little bit above the standard model, but then it drops to 0. Okay? So if you really have a low-energy string scale, by doing this study, you have some real hope to see something interesting, because you would see R not rise above the standard model, but actually be lower than the standard model. And what we have here are a couple of different string behaviors. And in one case, you see that you get a sort of a resonance where you have this resonance. In another case, you see that you don't even see a peak here, that it already starts to drop. So the message there is that you actually have some hope of not only distinguishing string models from a Z prime, because for a Z prime, you would see the cross-section is correlated with the R behavior. In the case of string models, of course, we know that it just goes to 0. So it's really quite different. So this is just the statement that you're not going to see string theory and black holes in the same time because it requires a perturbative string coupling. Okay. So this is just an aside. And I'm going to skip higher dimension operators, unless there are questions. So what are the distinguishing characteristics if related to jet gravity? Well, perhaps the energy dependence. Another really interesting, and as we saw by looking at both energy dependence of cross-section, energy dependence of transversality, we can not only hope to see new physics, but we can hope to actually get a handle on what that new physics is at some level. And by studying it in as much detail as we can, we hope to learn more in detail about what's going on. Another very interesting thing to look at will be leptons versus jets. Because if you have a black hole, which is classical, you have a very different distribution of final states than if you have something that really is just, say, a 4-fermion operator. So you can get a small difference in effect because of that. But even more dramatic, if you think about it, when you collide together two protons, you're colliding together quarks. When you collide together quarks, you don't expect to get leptons in the final state, unless somehow the object neutralizes. So if it really went through some strong quantum gravity effect, maybe you could actually shed charge, in which case you would have a much bigger cross-section for leptons than if you just had some ordinary scattering process. So looking at leptons versus jets can give you a lot of insight into what happened as well. And this is just to say that leptons are highly suppressed ordinarily compared to jets, just because you're starting off with quarks, not quark-antiquark in this case. You also have alpha suppression from interference. However, if you have black holes, your cross-section for leptons is much higher than we just saw, and it's well above the lepton background. So if you really formed black holes that were neutral, really neutralized all that QCD charge, you would find a much higher production of leptons than you would from ordinary QCD processes or even 4-fermion operators. So to summarize this part of the talk, black holes are definitely not as spectacular as advertised. The cross-section is so low that I don't even think we form them. Okay? And you certainly don't have multi-particle final states. There's just no, I mean, we really worked as hard as we can, given the experimental constraint, to say, do we ever get multi-particle final states? It's just not really happening. But there's a lot of information buried in 2 to 2 if we have a low quantum gravity scale. The rate as a function of energy is very important, but even more interesting is this R behavior, which you could really hope to distinguish different models of what's going on. Certainly string theory would exhibit a very different behavior than just ordinary quantum gravity or Z prime. And also looking at this threshold behavior could tell us even more about what's actually going on. And I think there's some work to be done here for the future. We really want to be able to do these studies and experiment of energy-dependent angle studies versus jets, not assuming any particular form of higher dimensions, but really just doing an unbiased study of what's going on in the cross-section, what's going on in this parameter R for both jets and for leptons. It could be extremely interesting. From the Monte Carlos, as I said, you want to allow these decays solely to 2 particles. Maybe the remnant is all there is basically what I'm saying. The question is, do you shed the charge in the initial state? And that gives rise to different distributions of final states. For theory, maybe we want to look at string theory models, and all these questions about do you shed charge are really interesting theoretical questions. They're not that easy. And there's other possible signatures that people might want to look into as much. But the goal, again, is to really just face the facts. I mean, we would love it if it was classical black holes. It just doesn't look like that's what it's going to be. So we really have to think about what will be there at the LHC, what could be there, and what would the signatures be. And that's what we tried to focus on in our work. And it looks like these compositeness studies could be an extremely interesting way, particularly if you actually identify KK resonances, to get an additional handle on what's going on with quantum gravity. Okay. So I'm going to end this talk here. And the final talk, which is this afternoon, I'm going to talk more about what this flavor structure is, which I think is extremely interesting because the sort of generic predictions are quite nice and probably a little different than what you've been thinking about before. So, thank you. Yes?
I have a question to this the sharpness of the production threshold for the black holes, because before you pointed out that the inelasticity really can change the threshold, and is the inelasticity not a quantity which is event by event, so which would smear out the threshold such that you don't get it?
Yeah, so that rapid rise, we don't believe it. It was just a model. It was just to show. I mean, basically, at some point, we believe the cross-section will be higher. The actual threshold behavior, we don't know how to predict. So it could be much softer than what that plot shows. It was just a very crude model just to show roughly what's going on. So again, all of this is just models. We don't believe either one of them. We don't believe the string model. We don't believe the black hole model. It's just a way of indicating that there could be very we were just thinking, like, what kind of qualitative features can show up. And so the interesting things to look at, to go back and understand what's really going on, are the threshold behavior, are the cross-section, are this parameter R as a function of energy. We're just saying what are the interesting things to measure and what might it tell you about what's going on at a fundamental level. Okay? Other questions?
Question that can the black hole produced by LHC can carry quantum number, color quantum number?
Sorry?
Can the black hole carry?
Yeah, so black holes can carry. That's sort of the question about this shedding of the charge. So first of all, as I said, we don't even know that it's really a black hole. So what I really think is most likely is that you collide together 2 quarks. You have something that carries the colored and charged quantum numbers of the quarks, and then decays to 2 quarks. That's the most likely thing. If there's some really strong quantum gravity effect going on, maybe it radiates something that sheds the charge. You're left with some gravitational object, which then could decay equally into L plus, L minus, and QQ bar. I mean, that's sort of the question we're trying to ask experimentally, because we don't know the answer.
Okay, thank you.
Okay. So we'll talk about flavor in a couple of hours.